Quantum computing has set itself up for a very narrow future as a supercomputer. An alternate future for quantum computing is for it to be much like classical computing, where classical computing takes on a broad range of different roles, not just that centralized supercomputing role.
Can you put a quantum computer in a satellite, car, or even laptop? It's possible with diamond-based quantum technologies that work at room temperature. Nitrogen-vacancy center qubits challenge the notion that quantum computing is confined to massive data centers. Find out how soon we'll have 64 mobile qubits and why you'd want them in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the co-founder and chief scientific officer of Quantum Brilliance, Marcus Doherty. Welcome to the show.
Hello, it's my pleasure to be here.
Yeah, thanks for joining. We like to explore different modalities from time to time. And I guess today we're going to talk about one we don't really talk about very often. So I'm happy to have you for this. I guess let's start with exciting high level. What modality are we talking about for Quantum Brilliance's machines?
Who Quantum Brilliance is that we're the company seeking to deliver mass-deployable quantum technologies. And when we think about quantum technologies, that could be everywhere. So this is quantum computers that could be in your laptop, in your workstation, in your car, in your satellite, etc. Or quantum sensors, which could one day be in your phone to tell you where you are, or are in a mining vehicle to navigate underground. There is really only one modality that is a platform that enables all those technologies to be real. And that is diamond-based quantum technologies, and in particular, the exploitation of the Nitrogen-vacancy center as the qubit that builds these different quantum technologies.
Yeah, so that allows for room temperature, right? Technology.
Exactly. So NV centers operate entirely in ambient conditions. So this is both room temperature and pressure, which is unlike nearly all other quantum technologies. And even in those conditions, they have exquisite properties. So at room temperature and pressure, NV centers have coherence times longer than a millisecond, which you know is 1,000 times longer than a superconducting qubit at cryogenic temperatures, and approaches what trapped ions and neutral atoms are, even though they are at very high vacuum. And the other distinguishing features of diamond is that not only does it have these exquisite properties, it is also miniaturizable. So this is an atomic scale qubit, which can be fabricated in a variety of different device architectures, which are all intrinsically small. So the node size is on the nanometer scale, very similar to where we are at with classical transistors. So you can think of having millions of these qubits in one device, either to be a sensor or a computer. And then the third element is that the control systems that run these qubits are also already miniaturized and ruggedized. So we use simple optics and also microwave and radio frequency control, which has already been matured by 5G in the radar industry to be able to build these technologies. So they have this very clear pathway to being this compact, miniaturized, robust technology that can really be ubiquitous.
Yeah, I was going to ask you about the control requirements. So even though we're not going to be chained to the giant, steampunk chandeliers that we're all used to seeing, there is still going to have to be some kind of wiring and control circuitry. And what would that, just to help listeners visualize, what would that really look like? For, let's say, per 100 qubits or so?
Yeah, exactly. So to give some examples today, so one of the things about diamond quantum technologies, which I think isn't fully appreciated, is they're already quite high TRL. So we have, say, Bosch, as an example, have developed a quantum magnetometer, which is the size of a Raspberry Pi. And so all of the control systems, everything is in that one Raspberry size Pi board, and that is delivering performance as a magnetometer. Companies like QDM, Diasense, are building quantum microscopes, which enable you to image things which you otherwise can't image at the nanoscale, and that is a microscope the size of something on your bench, including everything associated with it. Right now, our quantum computers, the Quantum Brilliance builds, is a 9U 18-inch rack unit, so it's the size of a large desktop computer. And those computers can be directly slotted into data centers, and indeed we're about to deliver 3 of those to Oak Ridge, where they're directly inserting them into their racks in their high-performance computing center. That's where they are today. Now, there's no reason why we can't get to a future where diamond quantum computers are a single board processor. So just like Bosch have achieved a Raspberry Pi single board sensor, there's no reason why we can't get there with quantum computers as well. And so indeed, that is what Quantum Brilliance is engaged to do. So the Cybersecurity Agency in Germany has asked us to deliver a mobile quantum computer by 2028. And our aim is to get a 64 physical qubit unit, the size of a GPU processor, delivered on that time frame.
Okay, so by 2028, you're shooting for a mobile 64 qubit quantum computer. And when you say 64, is that physical or logical?
So here it's physical. And then 2034 is where we're aiming for 64 logical qubits in that GPU size processor.
In that size. So is there a separate timeline in mind for just achieving high qubit counts that don't have to be mobile, like a 9U rack kind of thing?
So there is 2 tracks. One is the HPC market that we're aiming for, and that is around mass parallelization. So this is where you have many quantum computers which are operating in parallel, which is incredibly important for things like machine learning, where you have to distribute training tasks across many processors. Also incredibly important in the longer term with logical qubits for things like molecular dynamics, where you have complicated chemical systems, where you actually are breaking that system into many subsystems, say individual molecules which are reacting with each other, and then you're passing each of those individual molecules to a different quantum processor to simulate the chemistry, whilst you're using classical processors to simulate the trajectories of the molecules. So the reason why we work with HPC centers is that world of mass parallelization. Our current aim in that world is still to deliver that GPU-sized computer, but to now integrate these into compute nodes. So to build compute nodes that then go into a rack unit, which then goes into a massively parallelized system. So in the future, we may build specialized compute unit nodes, but right now, with our vision for 28, 29, etc., is to build a common unit and then otherwise combine it and build it into different types of compute nodes for HPC. That one unit could then go to edge applications. So this is now where we are taking that unit and looking for those applications in autonomous vehicles or in personal computing or in workstation computing and these sorts of things.
To simplify it a little bit, some approaches for scaling involve interconnect to kind of have each module combined to create one quantum computer realistically, right? So, like PsiQuantum, 1 million qubits. That really means you have a whole bunch of little photonic boxes inside that have a certain number of qubits, and you add them up, you get 1 million, and it acts like one, in theory, 1 million qubit computer. Is that the approach here, or are you taking some kind of more, almost like NVIDIA approach, where you have these things each being handed tasks, like you say? So it's not truly interconnect. It's more like you do this, you do this, you do this. We're not looking to hit 2,000 qubits as one cohesive device. Does that make sense?
Yes. So exactly, that's the sort of a differentiator in the intermediate term. So in the intermediate term, we will build quantum computers, which will first be 64 physical qubits in that small form factor, then 64 logical qubits, and then we'll continue to scale. So right now, we haven't identified any reason why we can't scale to very large qubit numbers and retain somewhat in that small form factor. And so we see a pathway similar to what classical microprocessors went through, which is to steadily increase the qubit counts whilst keeping the overall form factors of what we're doing similar over decades. So yes, in the far future, very large qubit counts in these small processor units, but in the intermediate term, these intermediate qubit counts, and then these are connected classically with each other. And then you not only have a couple of these, but you have many of these, which are then working together with those classical interconnects.
Yeah, and it sounds like you have some of a hybrid thing going on anyway, right? You've got some traditional HPC doing some work too, so it sort of all fits into that model, I'd imagine, right?
So yeah, exactly. So one of the things that we are doing with Oak Ridge National Laboratories is actually together working out, well, what is the pathway here in terms of hybridization, parallelization? What are those really important questions about when do you parallelize and why do you parallelize computation, or when do you hybridize between classical and quantum processors? And what we're delivering to them is a workhorse to answer those questions, which is a stack of 3 nodes where each node has a CPU, a GPU, and a QPU. And these are connected through fast buses, and then they're connected through Ethernet between the different nodes. And so that gives a flexibility to answer these questions about, well, what's important? How is information shared and what constrains computation? How do you make these asynchronous processor units talk to each other? And then where does that lead in terms of, if I had 1,000 units, what should the architecture be for that computing system if I had 1,000 of these units?
Someone at a trade show once asked me, how long before I have a quantum computer in my pocket? Just like as a quick answer, I said, well, do you have a supercomputer in your pocket right now? And he said, no. And I'm like, well, are you ever going to have a supercomputer in your pocket? Like, there are certain tasks that we do in data centers, right? Like, because they're so power intensive or they take time, and it's just not something you need to carry with you. But it does sound like you want us to carry one day, or you imagine us one day carrying some kind of QPU. And I totally get it for sensors, right? Like, they belong in the field. They belong where the sensing is happening, right? Obviously. So I was just wondering what you envision as a use for a quantum processor that's like right where you are, and not necessarily what we typically expect right now, where, oh, you have an app that'll make a call out to the cloud, run the thing, and come back to you, like that sort of approach.
I'd like to answer that question in 2 different ways. So first is more of a question of principles and where does quantum computing and how can quantum computing deliver value? And then I'll answer it in terms of, well, what is the vision for how this fits into the broader communications and computing infrastructure that we all live today? So talking to the first one, I think quantum computing has set itself up for a very difficult job. And one where it is a very narrow future for quantum computing. So at the moment, where most quantum computing modalities is leading is quantum computing as a supercomputer. This idea that we are building these machines which are going to be equivalent to entire classical computing systems and are going to be exclusively in the context of high-performance computing or supercomputing. That is a very narrow future for quantum computing, and one where, honestly, the market isn't that large. An alternate future for quantum computing is for it to be much like classical computing, where classical computing takes on a broad range of different roles, not just that centralized supercomputing role. And that we have data centers, but data centers are different to high-performance computing centers. They're different to supercomputing centers. Data centers have to manage flux of jobs, where there's many, many jobs coming in all the time and they're being distributed and run. And it's really important to have that flexible infrastructure to be able to respond to jobs. That's not what the future of quantum computers will enable if we are talking about 1s and 2s and 10s of these quantum supercomputers. Rather, you need millions of quantum computers, which, just like we have millions of classical computers and data center infrastructure today. And then also there is all those applications where we see computers outside of data centers and HPC, in our cars, in our aeroplanes, all the other places that we find computers, in the laptop that I'm using today. So where I see Quantum Brilliance doing is we are trying to deliver that much bigger picture for quantum computers, which is outside the narrow realm of supercomputing, which is actually to deliver across that entire compute infrastructure, and where we don't need to outperform the Summit supercomputer for our device to be commercially relevant to people. We just need to outperform their current computer that they're using for that current set of tasks, which is something which will be the size of a GPU or a CPU. And when we outperform that, we will have delivered value to the customer.
That opens up the thought of newer use cases and newer algorithms, right? Because obviously the biggest difference between a quantum computer and your laptop is, I guess it's not really correct, but you could say because your laptop's more Turing complete, if that makes sense, right? It does everything, whereas a quantum computer can only do the things it can do. I like to joke, you're not going to run Word on a quantum computer. You probably won't. So what types of use cases are you envisioning then? Do you have any in mind? Or is there like a branch of your company maybe that's going to start focusing on the research of these use cases and algorithms to step outside the view that we have? Because right now, let's face it, it's a lot of optimization, a lot of like machine learning problems related to actual, quantum machine learning, and then some kind of simulation. And basically, if it's not one of those three, it's not quantum right now. It's just not. So what are you envisioning?
Yeah, absolutely. So the primary use cases we are thinking about, the ones that would sort of motivate us to do what we do, is an easy one to talk about is machine learning. So we did work with Lockheed Martin Corporation, which was about solving an incredibly important problem that occurs in synthetic aperture radar. So around the Earth, we have these satellites which are orbiting, and they are listening for radio waves. And they constantly collect these radio waves, and then by sharing information between them, they can then build an image of things which are scattering radio waves on the surface of the Earth. That is a canonical machine learning problem, which firstly has some challenges. There is a real paucity of data. So let's say we're seeking to identify ships on the ocean. There isn't that much data for the synthetic aperture radar cross-sections of ships on the ocean. So there's a paucity of data. There is also a need to constantly evolve and update the neural network as additional ships or ships change as well. And so there's a need to have a degree of training efficiency to be able to be dynamic in that learning task. And then thirdly, it needs to be embedded on the satellite. So the quantum computing actually needs to, the computing solution has to be on that satellite in order for it to really achieve its function of being able to do onboard compute, so that when it communicates back to Earth through a constrained communication channel, it can do so efficiently. And so this is a prize example of a task where you need local compute, and it needs to be compute in a way that can perform these sorts of feature classification tasks efficiently.
Yeah, that's a great example. Yeah.
And so this is the picture where you would have training. Initial training would be done in a parallelized cluster, and then you would have your quantum computers deployed to the satellites, embedded in the satellites to do inferencing, and then to update the training through the mission. So that's one example.
Yeah. So to use kind of an NVIDIA parallel here, the biggest NVIDIA machines are being used to train, LLMs, let's say, or sometimes mine Bitcoin, whatever. But the graphics coprocessors locally are doing just like gaming or maybe some minor subsets of things. So the super version still exists, but you've got these like smaller ones. So you're seeing something like that where maybe on a phone you'd have your CPU, GPU, and your QPU, and the QPU would be invoked for very specific tasks, right?
Yeah, and so Hey, I think the idea of a phone-sized diamond quantum computer is a long way away. So I don't
Yeah,
want
of course,
to oversell it.
of
But
course, yeah.
a card that's in your laptop is something I can definitely envisage. So
Okay.
it would be part of a accelerator mix, right? So you'd have your graphics accelerator, you'd then have your quantum accelerator, you have your CPU, and you may have other accelerators as well in that future laptop. And the sort of task that I'm talking about here is then that machine learning example, where
Mhm.
as we do more inferencing local, it will be advantageous to have more AI accelerators that are local to you as those inferencing becomes more difficult and challenging. And so that would be a good use case. But there's other very important use cases. So I'll talk about another, which is at the moment we've really thought about quantum technologies being these very distinct things.
Mhm.
Where quantum brilliance is trying to bring things is much more similar to the silicon classical electronics industry, where you have a technology which was fabricating transistors in silicon, which can be used to build many different technologies, being end technologies, being sensors or integrators or adders or processors. And so here we see the NV center as that core unit, which can then be assembled in different ways. As an example, right now you can build sensors and processors, but what would be coming next would be an integrated processor sensor. And let me give a real example of what that could be used for. So there's a company called Protiviti Technologies, which is developing a compact point of care pathology instrument based upon diamond quantum technology. So this is where you would go to your doctor and they suspect you have low blood iron. And they go, geez, if I can do a blood test, but it's going to take days to get back to you, by which point you're probably a lot worse. And so what would be good is if I could work out what your blood iron is right now. The technology that Phoebe has developed is a shoebox-sized system where the doctor would take a prick test, they would insert that blood into a microfluidic chip, which flows over a diamond, and that diamond, the NV centers that diamond performs nuclear magnetic resonance spectroscopy in order to measure how much blood iron there is in the blood which is flowing across it. And this is a technology that's real. They're going into clinical trials with this technology. Where we see a sensor processor is where you go beyond just blood iron. Let's say you also want to measure calcium or another chemical in the blood. And now you've got quite a complex nuclear magnetic resonance spectrum from which you need to infer the presence or absence or the concentration of different chemicals via the correlations of different spectral lines in that nuclear magnetic resonance spectrum. So that's an example where a relatively small scale quantum processor, which is conjoined with the sensing system, could deliver that solution. And so again, I'd like to think of this a bit more broadly about quantum technologies and how they can be combined and work together.
Yeah, because most people just think of it as quantum computer, then you've got a quantum sensor, and quantum networking will connect them, and that's it. Like no one ever thinks about really, you might actually need the computation to occur there at the edge device, right? It makes sense. Everything else becomes an edge device. Why not? Why not some level of quantum computation? Quantum repeaters, those are application-specific quantum computers of a sort. So these are also application-specific quantum computers, right? I mean, they're being built and for purpose and designed. Because it's room temperature, there's much less power requirement. We don't have to worry about cooling. We don't have to worry about all that. Do you see that then also helping make the case for quantum as a true green energy, green like technology, right? Because we still, even though they're faster, they will be faster at certain things. We still have to worry about all the cooling and all that stuff. So is that your hope that you can truly say that you're using less power?
Yeah, absolutely. So I think that so we've for a long time advocated now that when you're thinking about quantum advantage, you also need to think about size, weight, and power as a comparable. So really If I'm a person who's building a compute solution, I have a certain budget for size, weight, power, and cost for my compute hardware to deliver that solution. That's whether I'm an HPC engineer or whether I'm an automotive engineer or whether I'm an edge device engineer. And it's when you're thinking about quantum computing versus classical computing, it is in those constraints, does the quantum computer outperform the classical computer? Now, in the future data center and HPC world, power constraint or power budget is going to be one of those critical things. And so where we see ourselves is not being able to only outcompete classical computers against power, but then also outcompete other quantum computer modality for that against that power dimension and fitting those constraints for that future infrastructure.
Yeah, I mean, right now, LLMs are a great example. They're talking about building nuclear power plants next to every data center. I mean, there's a reason for that. It's an immense power draw. And do you envision then that in the future, when you try to scale these up, you're going to have to develop entirely new error correction schemes? Or is this modality kind of able to build upon the codes that we already know of?
Yeah, so that's work that we're seeking to kick off with a few partners. So, in some ways, very basic error correction codes have been implemented on diamond quantum computers. But with our architecture and how we scale up, it requires, it has its own constraints around timing and how to measure syndromes and when you can measure syndromes, which is much more analogous to neutral atoms than it is to superconductors. So with neutral atoms, you need to transport and weight and then measure, and often you're doing a lot of post-selection based upon measuring after the circuit is executed. That's quite similar to diamond. So it's going to be a case of transporting, storing in quantum memory, and then measuring and then doing your post-selection is one of the key elements. And another key element is then being able to deliver fresh and reinitialized qubits from another reservoir of quantum memory. So in some ways, it's quite analogous to neutral atoms. But I think the key will be to begin with the neutral atom codes and then adjust them for the particular constraints of diamond processes.
And one thing about what you mentioned earlier with this idea of the QPU being right there at the sensor, is there going to be then a whole new class of advantage papers waiting to be written? Like we have this microprocessor working with a quantum sensor, and then we have this micro quantum diamond processor working. Like, is it going to be that kind of thing, like benchmarking what fits inside of a form factor, what fits and uses a certain amount of power, et cetera?
Yeah, well, absolutely. So that's what, we're hoping to equip the world with. So, right now you could even get started. So we have a software development kit and an emulator you can download from our website. We were one of the early software partners with NVIDIA, and it was really around building a software framework that enables people to really do this idea of embedding and parallelization. So to go, okay, well, can I really distribute my code and have my code run in parallel, and how do I manage running things in parallel or running things in a tight embedded loop and understanding what is happening there? So our software tools enable you to do that. And also our software tools enable you to emulate our current and our future processes as well. And so people can already get on board and have their vision of, well, what could this compact miniaturized processor or processor sensor do, and use our software to then simulate it and get performance data, which includes the accuracy or the outputs, as well as the timing information about how different tasks were timed and would run on the actual physical device. And so be able to write those papers about, okay, well, this task would take this amount of time with this amount of power, and this is the results we got from this task, and we can compare this with an equivalent system.
Yeah, that's really exciting because in theory, someone in oil and gas, someone in aerospace, whatever, they could just right now go and start playing around with your SDK and see if there's already an application they can experiment with, right?
Yeah, absolutely.
That's pretty great. And one final question, I guess, with this whole approach. are they more tolerant for errors? Like, do they need to have so many nines in terms of accuracy to be usable, or is that not really a thing? I mean, these aren't deep. I'd imagine they're not very deep circuits running, right? For these like onboard kind of communications. Most people probably wouldn't think of that, right? Like you're not doing anything that's going to be this really long, complex process.
No, I think we have to achieve similar fidelities as others, right? I think to be useful computers, even if they're physical qubits or if they're logical qubits, we're going to have high quality qubits. So, and where diamond qubits are today is 2 nines for 2 qubit gates and 4 nines for 1 qubit gates is where we are today, these aren't physical constraints, these are engineering constraints. And so there is more work to be done, but certainly Diamond is heading in the right direction to achieve the sort of quality factors you need to do performant computing. So
to be useful then, it has to be able right now to run a few shots, I'd imagine.
Yeah, absolutely. So, the quantum computers that we have, you can run. These are small quantum computers, the ones that we ship today. So the devices we are sending to Oak Ridge only have 2 qubits, but they're in that form factor. We'll be looking to tens of qubits next year, and then on to 64 in 2028. These are fully capable quantum computers. You can compose circuits, run circuits. You can choose what shot numbers you want. You can do what you need to with those computing systems.
Yeah, so like we said, there's a way to start playing around with this concept of onboard small diamond quantum computer today. So that's very exciting. And I imagine just about any laptop could simulate the numbers of qubits we're talking about. So I think it won't be a problem. Marcus, yeah, thanks so much for discussing your company's modality, and sounds like some exciting stuff coming. Thanks.
Great. Thank you. Thanks for having me.
That does it for this episode. Thanks to Marcus Doherty for joining to discuss Quantum Brilliance. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.